Twisting reality. Atomic sheets unlocking the doors of advanced technology. A collaborative team of physicists in the School of Arts and Sciences have found that putting a twist on tungsten disulfide stacks illuminates new approaches to manipulate light. The way light interacts with naturally occurring materials is well understood in physics and materials science. But in recent decades, researchers have fabricated metamaterials that interact with light in new ways that go beyond the physical limits imposed on naturally occurring materials. Metamaterials and their limitations. A metamaterial is composed of arrays of meta-atoms, which have been fabricated into desirable structures on the scale of about 100 nanometers. The structure of arrays of meta-atoms facilitate precise light-matter interactions. However, the large size of meta-atoms relative to regular atoms, which are smaller than a nanometer, has limited the performance of metamaterials for practical applications. Innovative research in metamaterials. Now, a collaborative research team led by Bo Jen of the University of Pennsylvania has unveiled a new approach that directly engineers atomic structures of material by stacking the two-dimensional arrays in spiral formations to tap into novel light-matter interaction. This approach enables metamaterials to overcome the current technical limitations and paves the way for next-generation lasers, imaging, and quantum technologies. Their findings were recently published in the journal Nature Photonics. It's similar to stacking a deck of cards but twisting each card slightly before adding it to the pile, says Jen, a senior author of the paper and an assistant professor in the School of Arts and Sciences at Penn. This twist changes how the entire deck responds to light, enabling it to exhibit new properties that individual layers, or traditional stacks, do not possess. Kim's insight on tungsten disulfide layers. Bumho Kim, postdoctoral researcher in the Jen Lab and first author of the paper, explains that by stacking layers of a material called tungsten disulfide, WS2, and twisting them at certain angles, they introduced what's known as screw symmetries. The magic lies in controlling the twist, Kim explains. When you twist the layers at specific angles, you change the symmetry of the stack. Symmetry, in this context, refers to how certain properties of materials, like how they interact with light, are constrained by their spatial arrangement. By tweaking this arrangement at the atomic scale, the researchers have bent the rules of what these materials can do, and by controlling the twist across multiple layers of WS2, they created what's known as 3D nonlinear optical materials. Screw symmetry and its implications. The researchers found that screw symmetry enables new selectivity for the light's electric field in the material, a part of light that determines its direction and intensity. Kim notes how they found that screw symmetry enables a new kind of light generation in twisted 4- and 8-layer stacks, counter-circularly polarized third harmonic generation, wherein light travels in the opposite spiral direction, a quality not seen in constituent WS2 monolayers. Adding an artificial screw symmetry allows us to control nonlinear optical circular selectivity at the nanoscale, Kim says. Experimental verification and potential impacts. In testing this technique experimentally, the researchers verified the predicted n-online arities inherent in various configurations of twisted WS2 stacks. The team observed new nonlinear responses and circular selectivity in twisted WS2 stacks that cannot be found in naturally occurring WS2, a revelation that could have profound implications in the field of nonlinear optics.